Hi, my name is Antonia Krefeld-Schwalb, and this is a presentation at the virtual MathPsych, and I'm going to present you now joint work with Benjamin Scheibehan and Thorsten Pachur on parameter correlations in computational models of cognition. It is a very important application of computational models of cognition to estimate latent traits with model parameters. That allows to then test group differences on the latent traits or test correlations of the latent traits with other variables such as neural data or process data or even demographics. But this requires that the model parameters are independently and reliably estimated. And this project is now focused on the question whether structure dependencies in computational models may jeopardize these very important applications of computation models. We started this model by focusing a generic, something that we call the generic choice model, that assumes that behavior is often modeled with a choice between different options or different behaviors. And this model has often two important structures, and one is a subjective value function that determines deterministic subjective values to the different objects. And here we assume that the subjective value function is governed by the parameter alpha. And then the second structure is a probabilistic choice function that has a noise parameter, often called theta, that determines then the probability of choosing one of the options or showing one of the behaviors. Although these two functions are theoretically independent, the two parameters here called alpha and theta that implement the two functions often are correlated due to a partial redundancy of the two parameters. So consider, for instance, the two constellation of a generic choice model that here in our generic choice model has a power value function that is governed by alpha and the logistic choice function that is governed by the response noise parameter theta. And there could be two constellations with one with a large alpha parameter and small theta parameter, and a second constellation with a small alpha parameter and a large theta parameter that make very similar prediction in many situations. And then as a consequence, the parameters in the estimation procedures are correlated. And that this is common, I will show you now three examples of computational models of cognition. One is cumulative prospect theory, which is a model of risky choice; generalized context model, which is a model of categorization; and simple, which is a memory model. And we used Bayesian hierarchical methods to estimate the models and then illustrate the correlation by showing the correlation of the posterior distributions. And here you can see the joint distribution of the group level parameters of the noise parameter on the y-axis, and the parameter that governs the curvature of the subjective value or evidence function on the x-axis. You can see for all these three models that there is a very strong correlation between the two posterior distributions, and this correlation is also the strongest among all the other parameter correlations in the model. But one can ask now whether this correlation has negative consequences for the model, because much like in multicollinearity, this must not necessarily be the case for model fit, for instance, in the predictions of the model. However, I will illustrate in the following that it has negative consequences for the recovery of group differences, and it has negative consequences for the recovery of correlations with external variables. So for this, I did a choice simulation and recovery and parameter recovery study with the generic choice model that I introduced above, that consists of a power value function governed by the parameter alpha and a logistic choice function governed by the response noise parameter theta. And I simulated several 100 decision makers with individual differences on alpha and theta that are independent, of course. And for each of these decision makers, I simulated a bunch of choices between different alternatives. And I conducted 2 simulation recovery studies. In the first one, I simulated group differences on the different parameters and then tried to recover these differences with Bayesian hierarchical methods. And in the second simulation, I simulated correlations of the individual parameters with external variables that I then tried to recover. So here is my setup for the simulation of group differences. So for each of the 100 decision makers, I simulated 250 choices, and I did the same thing in 5 different conditions. And those conditions were as follows. So I had a baseline condition, and then there were 2 conditions, EA1 and EA2, where alpha was different in 2 steps from the baseline conditions. So in EA1, all the individual values of alpha were 0.1 larger than in the baseline condition. And in EA2, all individual values of alpha were 0.3 larger than in the baseline condition. However, in these 2 conditions, theta was the same as in the baseline condition. And in the remaining conditions, I did the same, but the other way around. So now theta was in 2 steps larger than the baseline condition, and alpha was the same. I then used this entire setup to simulate choices and then recovered the parameters with Bayesian hierarchical methods. And what you can see here is now the recovered difference on the y-axis for alpha here and theta here. So in EA1, remember, there was only a difference simulated on alpha and not on theta. So alpha should be larger than 0, and theta should be 0 in both conditions. But what you can find is that the difference on alpha was not recovered, but instead there was a difference on the theta recovered. In those conditions where theta was manipulated, the recovery was better. So the differences on theta could be recovered, and there were no false recovery of differences on alpha, or only small errors. In the second simulation, I now simulated correlations with external variables. So for both vectors of the input values for theta and alpha, I simulated an external variable that was here external theta, only correlated with theta but not with alpha, and external alpha that was only correlated with alpha but not with theta. Used the setup, simulated choices, recovered parameters, and estimated the correlations, and what I found is that the external variable of alpha was now highly correlated with theta, and theta was even less correlated with its own external variable than with the external variable of alpha. And alpha also was now correlated with the external variable of alpha, but still showed a higher correlation with the external variable of alpha. And you can see this here in the plot with the black dots being the input values and the red dots being the recovered values and the external variables on the x-axis. But our project didn't stop here by showing only the negative consequences of the correlation. We also implemented a few proposals or solutions to reduce the correlations. And these proposals can be sorted into different sets. One set was focused on trying to rescale the input of the choice function, and the second set was focused on changing the model of stochasticity. So we then implemented all of these different proposals first in our generic choice model, simulated choices, recovered the parameters, and calculated the parameter intercorrelation. And here for 3 different proposals of rescaling the value function, rescaling the differences, the calculative differences before they go in the probability choice function, and normalization, I found that they were not really successful in reducing the correlation, except for the approach to rescale the difference that reduced the group parameters correlation pretty efficiently. However, we tried out 2 ways of changing the model of stochasticity that were pretty efficient in reducing the correlation. In particular, we implemented a trembling hand error. So we left the response noise function but fixed the response noise parameter to 1. and implemented in addition to that a trembling hand error G that indicates a probability of guessing or basing the prediction on the probabilistic choice function. And the second approach was to implement parameter stochasticity on alpha. So instead of assuming that alpha is always the same across trials, we assume here that alpha in every trial is drawn from a normal distribution with an individual parameter alpha and an individual parameter epsilon that that governs now the individual stochasticity in the model. And these two proposals were very efficient in reducing the correlations of the group parameters and the individual parameters. And next we showed also, we will also show that these three proposals that reduced the correlations also improved the recovery of the group differences and improved the recovery of the correlation with external variables. Here, just as an example, the correlation between alpha and the external variable of theta, that should be 0. As you can see here, with rescaling the differences, it was very small, so almost 0, and also with the parameter stochasticity approach, it was almost 0. But only with the trembling hand error, there was still a negative correlation recovered that shouldn't be there. But the previous results were only based on simulated data in this very artificial generic choice model that I used. So next we implemented these proposals also in cumulative prospect theory, and here I will present you only the results of the three most efficient proposals. And all three of them reduced the correlations, and in particular, changing the model of stochasticity was very efficient in reducing the correlation. But what is even more convincing is that changing or adding parameter stochasticity on alpha, the curvature parameter in prospect theory, also improved model fit enormously, here measured with WAIC. And we also tested in a different data set whether group differences would be recovered differently with the model with CPT with parameter stochasticity. And indeed here, compared to standard implementation where a difference on alpha, the curvature parameter, was not observed, with when CPT with parameter stochasticity is used, there is a difference on alpha observed. And this mirrors very nicely my simulations with the generic choice model, where it was also very hard to recover differences on alpha with the correlation of parameters. Okay, so the summary of all this very briefly is I could show that there is a common source of parameter correlations in many computational models of cognition, and that these parameter correlations can have negative consequences on the recovery of parameters. We also proposed a few ways of reducing the correlations between the parameters. And herein, adding parameter stochasticity seems to be a very promising alternative error model that leads to reduced parameter interpolation, but also that improves model fit. And the conclusion of all this is that I think parameter correlations should be considered as an additional model criterion, and should also be considered whether maybe inferences in the past might change if models are used with less correlated parameters. And I think based on our results, the question about which error story is best should be reformulated to also consider the parameter correlation and not only model fit. And I also think that there should be new ways be developed to estimate parameters in constraint models with strong structural dependencies between the parameters. So for instance, adaptive design methods, or maybe also a search for optimal stimuli. So finally, thank you all for your attention, and thanks to my collaborators, Thorsten and Benjamin.